All right, so what we're going to look at today is we're going to look at a structure, a data structure called a heap, and some applications of the heap. All right? So is anybody familiar with the heap? Excellent. Heap? Maybe. All right. So on the notes, I have basically a link here. This is actually kind of a cool thing. This link right here, if you follow this link, you will actually get a bunch of visual images of people implementing sort. So you can see different ways of sort being implemented, different types of sorts, quick sort, selection sort, etc., etc. Okay. So let's talk about a heap. All right, let's talk about a heap, then we'll look at some heap applications, some heap analysis, that type of thing. A heap, basically you can say a heap is a complete binary tree. Complete binary tree with a greater than or lesser invariant. So greater or lesser invariant. And what the lesser or greater invariant means is that that's the relationship between our node, the key value in a node, and the node below it. So if I have a max heap, then the node which is above, the parent node, will be bigger than a child. So for example, 23, notice is bigger than 9, but 23 is also bigger than 11. Okay. And recursively the same thing applies. 11 is bigger than 2, 11 is bigger than 10, 9 is bigger than 8, 9 is bigger than 6, and 8 is bigger than 7. So we have at least this greater than invariant. Yeah, Scott?
Heaps not have multiple keys, duplicate. Sorry, duplicate keys.
Yes, they can have duplicate keys.
Oh, you can.
In fact, well, they can, and in some cases they often do, which is different than a binary tree. So, but it looks like a binary tree, right? Looks like a binary tree. But there's a special requirement, and that is the word complete. So make sure we understand what complete means, because it's absolutely necessary for a tree to be complete in order for it to be a heap. Here's how it works. Complete means that the tree, well, first of all, if a tree is complete, it's balanced. If a tree is complete, it's balanced. But if a tree is balanced, it may not be complete. So notice that in this tree, how many nodes do we have? 8 nodes, right? If I wanted to add a node, I would have 9 nodes. Okay, that's a very easy question. So the question is, where would I add that 9th node? Well, does this tree look to you like it's balanced? Yes. Yes. Balance means that what happens is every level in the tree is full, except possibly for the last level. So this is a balanced tree. I know that if you were to balance it, it would fall over. I get it. But that's the idea. It's called balance. So if I were to add another node, for example, here, if I were to add a left child to the 10, obviously to keep the invariant, I would make it a value like a 8, or a 7, or a 6, or a 5. That would still be balanced. Okay? So if I added a left child here, that would be balanced. If I added a right child here, what could I add as a value here?
Less than 6.
Give me the biggest value I could put in here.
5.
5 is correct. We use integers. That would still be balanced. However, adding a node here or adding a node here would no longer make the tree complete. Complete means that if the tree is balanced and there are missing nodes on the tree, they must be the rightmost nodes. So we fill the tree in one way and one way only. We're going to add the new node. The new node has to come here, so that if we have, for example, 9 nodes, then the missing nodes are the rightmost nodes at the bottom level. That's what a complete tree requires. So you cannot skip. So basically, there's only one location to add a node to. And right now, it's going to be the right child of the 8. And if we do that, we can go here, and then here, and then here, and then here, here, and here. That will be the sequence. If we have to delete a node from the heap, we'll go to the bottom level, and we'll hit the rightmost node. So it would be this one in this case. So adding node and deleting node basically adds them at the bottom level left to right. And removing them removes them at the bottom level, right to left. Clear? Yeah.
How do you know there wasn't already a node from the other side?
Over here. Well, if we assume that our heap, if we assume we have a heap, then it must be complete. And complete is a shape. Complete is a shape. So basically this shape is complete. The invariant is something else. But once we assume that we have a shape that's complete, you'll see how easily we can determine whether, well, first of all, we're going to, okay, let me put it this way. We're always going to assume that the heap is complete.
Yeah,
Yeah.
I guess my question is, how do you know exactly where to add another node to keep it complete?
Okay, I'm going to answer that question too. It's an excellent question. See, this is a thinking man over here. He thinks, and it's good. So that's exactly what we're going to be going for. So right now, let's just take it for what it is. So completeness is a shape. So how many different shapes do we have for a heap with 137 nodes? How many different shapes? If you're computing, you're working too hard. One. There's only one shape. And I'll tell you what the shape is. 127 of them are going to make a full tree. And then 11 will go on the bottom level. That's it. That's the shape. So a heap of 138 nodes, there's only one shape. A heap with 1,000,003 nodes, there's only one shape. For every number of nodes, basically you just get the power of 2 minus 1 to max out the fullness of it, and then add left to right the incomplete level. Okay? Shape. Okay, so this particular structure has two elements as part of it. It is complete because of the shape of the binary tree. Notice I didn't say binary search tree. It's not a search tree. Because notice here, we go here, 23 is bigger and bigger, and 9 is less than 11, right? But here, 8 is bigger than 6. So we cannot search using this tree at all. But it does have the proper shape, and it does have an invariant. Now, if we flip the invariant from greater than to less than, then we would have the smallest value on top, and the value would be bigger as we go down. Both children would be bigger than me. That's called a min invariant. But in this case, we have a max invariant. So if we have no replicates or no duplicates, we will have the biggest value in the top. Or if we have duplicates, we'll have one of the biggest values in the top. Right? And he's here. You is here. All right. All right, so now what we're going to do, we are going to, and this is very, very important, we are going to look at this tree, which is a complete tree, and we're going to number the nodes, starting at 1 for the root. Not 0, but 1 specifically. And then we're going to go what we call row major order. So row, 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 row by row. And we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So 9 would be here. This is 10, 11, 12, 13, 14, 15. We're going to number the nodes, starting at 1, row major order, from the root. Once we do that, you're going to see that we're going to be able to identify the root as node number 1, and that's a 1 right here. Then we're going to look at the fact that 1's children are always going to be 2 and 3. So you can see over here that I went the wrong way. That the left child of the root is node index 2, and the right child is index 3. But we can generalize that to say that the children are actually going to be 2 times the index of the root, or I, if the root is 1, and 2i plus 1. So double I and double I plus 1, and you'll see this pattern continues for any child. So if my index is, I'm going the wrong way each time, okay. If I go from 1, I double 1, I get 2, left child. I double 2 plus 1, 3 is the right child. If I double 3, I get 6, that's the left child. If I double plus 1, I get 7, that's the right child. If I double 4, I get 8. If I double 2, I get 4. So for any number, if I give you the index of the node, you'll be able to tell me the indexes of the left child and the right child immediately. And I can also find the parent, because the parent is nothing more than taking the index of the child dividing it by 2 and taking the floor function. So 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 5 divided by 2, floor, is 2. 7 divided by 2, 3.5, floor is 3. 3 divided by 2, floor is 1. So we can navigate by indexes, which makes us think, why are we doing that? And the reason we're doing that is because implementations of heaps are not, they are logical trees, but they are physically implemented as linear structures like arrays. Okay, so let's talk about, so we'll come back to the implementation and all that kind of stuff. So let's look at a process called max heapify. Max heapify means we're going to fix a near heap, or something that's almost a heap, back to the invariant. So again, we're going to assume the shape is perfect, that the shape is complete, okay? And we're going to have some kind of violation. Well, a violation will occur, for example, if I had, let's see what I had over here. So if I had a 3 up here instead of, well, let's see what I had here. I actually had a 23 here, okay? So let's suppose I had, let's see how I did it here. So at this point, notice that if this 3 was on top for some reason and 23 was here, we could exchange the 3 with the 23 and not the 3 with the 11. And the reason for that is because 23 is bigger than 11, so 23 will make a good parent for the 11, for the max invariant, and then we'll switch the 3 downward. And then we'll see whether 3 is bigger than the 8 and the 6, and it's not. So what we're going to do is we're going to compare the 2 children of 3, which are 8 and 6, and we're going to switch it with the larger of the 2, which is 8. So 3 will go down, 8 will come up. So it's going to 8 here with a 6 as a parent is fine. 3 will go down, and then again 3 will have to be switched again. How many nodes are in this heap? 8. What is 8 divided by 2? Okay, what's significant about 4? It's a parent of 8, but what's more significant about 4?
The amount of levels.
It's the parent with the highest index. It's the parent with the highest index. So if I know that the number of nodes is equal to 8, and I wanted to find out if I have a right child, if the maximum parent has a right child, all I have to do is double the maximum parent index and add 1. And that makes 9. But 9 is bigger than n. What's n? Number of trees in the heap. Therefore, we can conclude that the maximum parent does not have a right child. So therefore, if this 3 is traveling here, and now it's swapping with 8 and 3 is here, I have to compare 3 against its left child and right child. But before I do that, looking at the index of 4, 8, and 9, I notice that 9 is bigger than n. Therefore, I only have to compare this 3 against the 7 to recognize the fact that there's only one child. This value is bigger than the 3, so the 3 goes down, 7 comes up. And there's the 3 traveling downward, and this 3 is going to go down one more time, and now I have fixed the heap. So if the 3 was up here, you can see that it's going. Now what is the complexity of fixing the heap, assuming that we have an incorrect value at the root? What is the complexity of fixing the heap, assuming we have an incorrect value at the root?
The height of the tree.
It's height of the tree, and which is? Because it's a complete tree, which is a balanced tree always, it is log base 2. Okay, good. See this tree? So that's enough of the tree. The tree is just something that shows us performance and the logic. But actually, heaps are never implemented as trees. Heaps are always implemented as arrays or linear structures. You can implement them on files. You can implement them as vectors. You can implement them as arrays. So you can see that there's a mapping function of the logical tree. That's why the 1 is actually the 1 index of the array. The 2 is here. The 3 is here. This is 4, 5, 6. This should be 7. It's kind of messed up. 7, and this should be 8. Got to fix that slide. All right, so you get the idea, right? So 1, 2, 3, 4, 5, 6, 7, 8. That's the idea. So now, if I were to erase the tree structure, and I put the indexes here, 1, 2, 3, 4, 5, 6, 7, 8, where's the parent of the 3? Well, this is 8. 8 divided by 2 is 4. 7, 6, 5, that's the parent. What's the parent of the 7? 4 divided by 2 is 2, that's the parent. What's the parent of the 8? It's going to be this one. So I can go up and down the tree, really, the figurative tree, using an array structure. So I don't need pointers. I need indexes and I need computation. Okay. Let's think about, so therefore, we can certainly assume that we have an array. And let's say we do have an array, something like this. Let's say we have an array. And the array has, for example, n elements. And we're going to index those elements, 1, 2, 3, 4, 5, all the way to n. And I'm going to randomly initialize these elements. Okay? And I want to know is how long is it going to take me to turn this array into a heap? Not only that, but I want to know how the heck do I do it? How do I turn this array into a heap? And what's the cost of it? So clearly, I can take 8 values and randomly put 8 different values in there, and then I don't have a heap anymore. I'll still have a complete tree, because by definition, the array is going to be a complete tree, by definition. And now, Ronaldo, you can see why we can't have a right child here, because a right child here, with a node of 5, would be the index 10, which would imply that 9 and 8 are going to be there, and they're not there. Okay, so if you had index 5, 1, 2, 3, 4, 5, then this would be 11 would be the right child, 10 would be the left one. But then if you have an 11, you must have a 10 and a 9. And if you don't have them, then you have holes in the array. And that's not allowed. And that's why we always know the length of the array, or at least we know how many active elements are in the array. Active elements. I could make an array of 1,000,000 elements, but only have 8. So n would be 8, so I could keep track of it. So if I wanted to add a 9th element, I would add it at the 9th position in the array, and that would make a complete tree of size 9. But then I'd have to make sure that I'm not violating the invariant. So I'd have to shift that into the proper location. We'll talk about how to do that. But to do that, let's find out how to heapify an array. So given an array A, so this is going to be given an array A and index I, we assume binary trees rooted at I are max heaps. So we're going to assume that we have a root, and this root has a subtree, and then another subtree. These subtrees are heaps, max heaps, but the root possibly is a violation. And we already know what we're going to do. What we're going to do in this case is we are going to do what? We're going to compare the root against its children. And if it is bigger than the children, we're done. Because if these are max heaps, and this is bigger than either of its children, then we have a max heap. But if it's not bigger than either child, then we'll compare which child is bigger, and we'll swap the root with the bigger child. The bigger child will then make a good parent for the other subtree, and then the node that we swap from the root will go down, and now we have to check that one. Is this bigger than its children? If it is, we're done. If it's not, we compare its 2 children. If it doesn't have 2 children, we'll compare 1 child. And we'll swap it with the larger child. The swap will always make the way you didn't go fine. But the way you did go, you have to check, are you now bigger than the other children? If you are, you're done. If not, you may have to continue swapping. So, what is the complexity of max heapify? Well, the height of the heap with n nodes is log 2n. Okay? We will swap from the I node down to node n, which will be less than or equal to log 2n. So the complexity of max heapify is theta log n. Now, what about building a heap? So building a heap is what I'm talking about here. So here's how we're going to do it. We're going to do it, it's going to be kind of a recursive build. It's going to work like this. So I have here, you see this is, how many nodes do I have here? 8. So I have an array of 8 elements, which automatically makes it a complete tree shape. because that's just the way we're going to assume it is. And then what we're going to do is we're going to say, what is 8 divided by 2? The answer is 4. We'll count 1, 2, 3, 4. This is the fourth node. So the fourth node is significant because it's the maximum parent. It's the parent with the highest index. So what I need to do is I'm going to compare 7 and 10. And I'm going to say, is 7 bigger than 10? And the answer is? No. It is not. So therefore what I'm going to do is I'm going to swap the 7 against the 10. I don't have to swap, I don't have to compare the 10 with its sibling because 10 doesn't have a sibling. And I know that because the maximum parent is 4. The maximum index is 8. There is no 9. So when I get the maximum parent, I say, hey, if I double it plus 1, is that less than or equal to n? No. Okay, then I only have one child. I don't have to check if I have one child. I know I have one child, otherwise this node wouldn't be a what? Parent. If it's a parent, it's got to have a child. But two children are not assumed. Okay, so I can easily find the maximum index of the parent. I can easily determine that there's no right child. So I simply compare the key of the child against the parent, and they are out of order. I will swap them. When I swap them, this blue triangle becomes a subheap. Now what I'm going to do from 4, 1, 2, 3, 4, I'm going to go down to node number 3, and I'm going to do the same thing. I'm going to say, are you, first of all, what's the index here? 3. Now, is 7 less than or equal to n? Yes. So therefore that means this node has 2 children. So I'll compare the keys of the children, and the bigger is 10, and then I will say, am I bigger than 10? No. So swap with 10. 10 comes up, 4 comes down, and now I have made the red triangle a subheap. Okay? What am I going to do now? I'm going to go to 2. When I go to 2, I'm over here. Keep in mind that I have a 10 up here. Notice that 19, is 19 bigger than 6 and bigger than 10? Then automatically green is a subheap. So I have now a subheap on the left side and a subheap on the right side of the root. So now my index goes from 4, 3, 2, now to the lowest index parent is always the root, that's 1. And I will say, is 5 bigger than, first of all, does 5 have 2 children? Of course it does, because 3 is the right child and 3 is less than 8. So therefore, we're going to compare the 2 children, and 19 is the bigger. Is 5 bigger than 19? The answer is no. So we're going to flip the 19 up. We're going to put the 5 down. The 19 is always going to be fine here because the bigger child can always be a parent on a max heap. The 5 comes down, so now we follow the 5. The 5 is at index 2. The right child index would be 5. Yes, we have it. So compare the 2 values here, 6 and 7, against 5. Violation, we swap it with, well, actually it should be a 10 here, right? There's a 10 here, I'm sorry. So 6 and 10, so we're going to swap the 5 with a 10. 10 comes up, find parent here. 10 comes up here. No.
19
5
5 and 7.
10 comes up here, 5 is here, 7 is waiting here. So at this point, so we have a 5 here. The index, the current index right now is 4. Double that is 8, so there is no right child. So we'll compare this 5 against the 7, which has traveled down to here. And it's a violation, so then we do that. So once we put the 5 down here, the index of the 5 is 8. But now 2 times 8 is 16. There is no 16. That means there's no more children. I'm a leaf. If I don't have a left child, I'm a leaf in a complete tree. Okay, so the question is, what exactly did we do? We recursively built the heap, but the question is, what is the complexity of doing that? Let's say I didn't have 8 nodes, but I had 8 million nodes. How long is it going to take? Is it going to take 3 milliseconds, or is it going to take 3 billion operations? It's an important distinction, right? So, what is the complexity of building a heap? So basically, what we can do is we can sort of count what the heck we were doing in the first place. The complexity of building a heap, let's assume a full tree. And again, a full tree is a good assumption because basically the tree is not full. It's always complete, which is almost full. Right? And the height is still asymptotically the same. So let's assume that we have a complete tree, a full tree rather. So the number of nodes, the depth of the node here is 0, the number of nodes is 1, and the number of comparisons is 3. How did I get 3?
The amount of levels, minus 1.
Okay, remember how we built the tree. Let's go backwards here. Assuming that we already finished this one, we came up here, right? Let's assume we have a full tree, right? Full tree would have 15 nodes, right? 15 nodes, so what do we have? We have log base 2 of 15 plus 1, it's going to be 4, which means the height is going to be 1, 2, 3, 4 all the way across. And that means we have 1, 2, 3 comparisons in the worst case. When we get to this point, remember, this is going to be a subheap, this is going to be a subheap, but this could be a violation and might have to travel all the way down to the bottom, which is going to be 3. And so therefore, that's what I'm trying to show you here, is that the number of nodes is 0, number of nodes is 1, depth of 0, 3 comparisons, 1, 2, 3. By the time we are building the heap and we get to the root, which is the last one to go, it might need 3 comparisons. When we are working backward, and we are, so what's the maximum parent here? Well, first of all, n is equal to what? 11, right? 11 divided by 2 is, 11 divided by 2, 5. 1, 2, 3, 4, 5. That's the maximum parent. 2 times 5 is, 2 times 5 plus 1 is 11, so we have a right child. So this maximum parent has 2 children. So of course we can fix that. We fix that, we fix that, we fix that, and let's say we're fixing this. When we're fixing this, notice there are 2 elements, 2 nodes at this level, right? And each of them, assuming a full tree, might need how many comparisons? 1, 2, to swap down to the minimum level if necessary. So therefore, we have 2 nodes at depth 1, and the maximum number of comparisons is 2. By the time we go over here, we have 4 nodes. The number of nodes is exponentially growing. 1 root, 2 children, 4 grandchildren at a depth of 1 more. Number of comparisons, only 1. And finally, when we get to the bottom, all the children, we have the depth is going to be equal to 3 in this case. The number of nodes is going to be 8 in a full tree, and number of comparisons will be 0. Because a node of a heap of size 1 node is a heap. No violations possible. Scott, you had a question?
Each subheap doesn't each subheap have to make 2 comparisons though? Instead of, like, you're saying there's
2
one?
comparisons is 1 comparison.
Okay.
Because it's theta, right? We're doing theta, complexity.
Gotcha.
Okay? So to compare whether you have a right child, to compare the value of the right children, to do the swapping, theta 1.
Okay.
Because it doesn't matter whether I have 1,000,000 nodes or whether I have 15 nodes, I will do the same number of operations to accomplish that task. Does everybody understand what these things are doing? So now what I need to do is, if you can see this relationship here, in general, what I'm going to do is I'm going to go from 1 to the height. I'm going to take the number of nodes at the depth I minus 1. So depth starts at 0. As I starts at 1, this starts at 0. So number of nodes times the number of comparisons per node at that depth. So I'm going to multiply 1 times 3 plus 2 times 2 plus 4 times 1, etc., 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 in general. So that's the general one, but I'm really going to go from 1 to h, or whatever the heck that is. So here is the model that we're going to do, that we have to solve. So basically what we have is we are going to go from 1 to LGN. Again, let's assume that our tree has 16 nodes. And again, 15, 16, I'm going to let it go as the same thing. I'm going to consider 16 to be a full node, full tree, just easier for analysis. So what I'm going to go is 2 to the I minus 1. That's going to be the number of comparisons, and that's going to be the number of nodes. So if n is equal to 16, LGN is going to be what? 4 minus 1 is 3. That's the number of comparisons, and the number of nodes is going to be 0. Get it? So this is going to be 0 times 3 in the case of 16. In the case of 1024, this is going to be 0 times 9. You get the idea, right? So this is the sum we have to solve, which is nothing more than 2i minus 1 LGN minus I, 2i minus 1. So it's this one, so we can split this into two summations. So this summation is just product of this times this, so it gives us two terms in the summation, which means we have a difference of the summation of this minus the summation of that. It's right here. So here's the first one, here's the second one. LGN is a constant, goes out in front, and so therefore this becomes a simple geometric series, the first term. And the next one is more of our I to the I minus 1 type summation. One easy way you could do this is multiply it by 2. If you multiply it by 2, you get 2 to the I 2 to the I, and then divide it by 2. And then just get the number and divide it by 2. It's a cheating way of doing it, but it's very, very effective. So easy to solve. So when we solve this, this is a geometric series. And this is basically this one here. So I'm going to solve it the long way. When I solve it the long way, I get finally, where is it over here? N LGN minus n plus 1. So now we can compute everything. And so when I simplify everything, is I get n LGN minus this. So it's going to be minus that. And it's going to be plus n minus 1 minus LGN. That is the complexity of building a heap. So the complexity of building a heap is unbelievably fast. It is linear. So it's theta n, where the number of actual operations will be actually less than n, but it'll be proportional to n. Does that make sense? So that's just a solution of this sum. That's all. So it's this, and then we have to solve this one. And again, this one you can solve much, much easier by just multiplying it by 2, getting 2 to the I 2 to the I, looking at the standard solution, then divide it by 2. Multiply by 2, divide by 2. The oldest trick in the book. All right. So that's what we have. So a heap can be built in linear time. Now, what is heap sort? Now that we know what a heap is, how is a heap sort going to look? And I will show you essentially what a heap sort is going to look like. It's a very simple idea. So what we're going to do, we are going to have a max heap. We can create from an arbitrary array a max heap in linear time. Okay? So now, what value is in the root? The maximum value is in the root. So we have a heap in linear time, and the maximum value is here. Now keep in mind, this is really an array. So that means that this element right here is physically here, and this element is physically here, right? That's where those two elements are mapped. Are you agreeing with me? So what we're going to do to the heap sort is we're going to take the element at the root and swap it with the last element in the array. So this is going to be, I'm going to call this big M for max, and I'm going to call this little s for some small value. Because it's going to be relatively small. It might not be the smallest, but it's going to be relatively small. So M is going to go here, and this s value is going to go here. So that's what's going to happen. So M goes here, and then s goes here. That's a swap. Now, what I'm going to do is the size of the heap is equal to n. I'm going to, after I do the swap, I'm going to say the size of the heap now is n minus 1, which means effectively I'm cutting off this element from the heap, which means effectively I'm no longer treating this element as part of the array. So what I have here is I have a small element, but this small element is sitting on top of a subheap, which is, on the right side we have another subheap. Are you with me? And we know, in order to fix this, all we need to do is swap it with the larger child and keep going until we don't have a violation anymore. Now, chances are pretty good we'll go pretty low with the swapping, because this element came from the bottom, which means it's relatively small, which means it's going to be smaller than the relatively bigger values up high. So it's going to basically go back down to a similar look, maybe to the bottom, maybe 1 or 2 levels above, who knows? We don't quite know where it's going to be. Once we do that, and that's going to take LGN time, to swap it down, it's going to fix the heap. Once I fix the heap, I will have the new max element here, and the S will go someplace in here. So what I'm going to do is I'm going to take this M, and I'm going to put this into this location, cut this from the heap after the exchange, and put from here the relatively small value here. And I'm going to repeat this pattern. And by repeating this pattern, the maximum value originally will be now in reverse order, going down to the smallest value. That's heap sort. Questions? Does that make sense?
The complexity for that is log n.
We didn't talk about that yet.
Okay.
We didn't, so that's the algorithm. That's what we just talked about. So we can look at those notes. So what is the complexity of heap sort? That's where we want to go. Complexity of heap sort is going to equal to the maximum number of swap downs at height equals I times the number of nodes at height I. So you can see over here we're having 2 to the k minus k, 2 to the 0, or one node. Okay. Okay. So and then the swap down is at the point we get here, the number of swap downs is going to be 0. Why 0? Because by the time I'm dealing with this one, it's going to be 0. Because it's only going to be one node, because I'm fixing it. Okay? When I'm down below here, notice it's going to be k minus 1, because basically when this thing goes up to the root, then it has to be possibly going all the way down to the bottom again. So that's why I'm going to have 2 to the k minus 1 nodes down here, and their work, which is the number of swaps, is going to be k minus 1. But each time I do a swap down, I cut one from the node. So by the time I address the root, by the time I get to the root, I'm done, really. Okay, so the solution is going to be the maximum number of swap downs at height I is going to be I minus 1, and the number of nodes is going to be 2 to the I minus 1. If we solve this one, we will get n plus 1 times LGN plus 1 minus 2n. So our comparison heap sort is theta n log n, which is not surprising because we saw proof last class that the comparison sorts require n log n at the very least. We did a very nice proof last time, right? From the lecture notes, right? So that's not surprising. So heap sort is going to very, very efficient. By the way, that is the worst case. It's also the average case, but it is the worst case. So it's not going to be any worse than n log n. That's different than which sort? Than a quick sort, which could go as bad as n squared. How about merge sort? Stays n log n, but requires twice as much memory. Okay. So what about adding elements to the heap? How do we do it? What's the complexity of an add? Well, to answer that question, I'm going to answer that question with another question. What is a priority queue? Well, a priority queue, many of you already know what a priority queue is. It is a FIFO queue, where elements go in from the rear of the queue and they get removed from the front of the queue. And that's a normal queue. It's a FIFO queue. So if you first in, first out. And that's the general idea of a priority queue, except that we are going to put you first in, first out, but we're also going to put you in the order of priorities. So if the priority 1 is the top, number 1 is number 1. So if number 1 comes in, number 1 goes out. If number 1 goes in and number 5 goes in, then number 1 is going to get out first. But if number 1 is still getting out and number 5 is still in the queue and another number 1 comes in, that number 1 bumps number 5. That's a priority queue. And if a number 2 comes in, it'll bump 5 but not 1. And then it'll come out in the order of 1, 2, 5. Get the idea? So, of course, if we have, for example, 1, 2, 5 in the queue and all of a sudden we get 5, 5, 5, 5, 5, 5, 5, those 5s are just going to line up behind the 5 and the 1 and the 2 will still come out first. So you get in queued next to next to the elements that have the same priority as you. It's people, it's priority. Okay, so that's a priority queue. Now, priority queue can be implemented in two different ways, many different ways, I suppose, but two of the most basic ways are, let's suppose we have two priorities, 1 and 2. 1 is top, 2 is lower. We can have two queues, right? So the queue of 1s, queue of 2s. Somebody comes in, are you a 1, go in this queue. Are you a 2, go in this queue. Then, to serve them, we will see, is the 1 queue empty? No? Then remove from there. Is it empty now? No. Then remove again. Is it empty now? Yes. Then remove from 2. So nobody gets out of 2 unless 1 is there. So that's, you can implement it using 2 queues, but that's with 2 priorities. What if you have 100 priorities? Then you need 100 queues. What if you have 1,000 priorities? Then you need 1,000 queues. So it's not a very scalable solution, but one scalable solution is to implement a priority queue using a heap. So let's take a look at how that might be done. So so a priority queue is a queue where the elements carry priority as well as a value. The elements are dequeued from the priority queue by highest priority. And again, 1 could be the highest priority. We know highest doesn't mean the biggest value. It could be low. Number 1 is the best, right? Okay, even though it's lower than 2. Okay, so let's suppose we want to build a priority queue with this structure here. So this is the array, by the way. Element 1, 2, 3, 4. Get the idea? So we have how many? 1, 2, 4, 8. That's 15. So we have 18 elements. So you understand this is a min heap. This is a min heap, right? But it's more than a min heap. It's also a priority queue. Why? Because if 3 is the lowest number, and that means it's the most important because 3 is close to 1, that means 3 is the first one out of the queue. So we're going to dequeue from this priority queue implemented as a heap out of the root. Okay? But before we do that, let's see what we would do to add something into the heap, into the queue, which is a heap, which is a tree, which is actually implemented as an array. All right, so we're going to add a new value in. Where's the new value coming in? Always coming in here, right? Always coming in here, which means coming in here. So we're going to add a value of 5. 5 is a relatively high number. So we're going to add the 5. So what's going to happen is the 5 comes in to the bottom of the array. It comes in as the right child of the maximum parent, in this case. And then we will compare it. Now, if you look at this, this is 19. 19 divided by 2 is 9. That's 9. Because the value is violation of the invariant, the 5 goes up, 46 comes down. The 5 goes up, the 26 comes down. The 9 goes down, the 5 comes up. It stays. So the 5 goes chick, 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 and we go chick, chick, chick. And so this is our result, right? You can see that that was pretty fast. In fact, the worst time complexity for inserting into it would be log n, because that's the height of the tree. All right? So now my question is, as we're running out of time, is let's do a simple analysis. We have a priority queue insertion analysis. Let's do a very simple insertion analysis. Suppose we have a priority queue with 4 priorities. 4 priorities. 1, 2, 3, 4. 1 is the best, 4 is the worst, etc., etc. And all of them are equally likely. That means that 25% of our elements are 4, 25 are 3, 25 are 2, 25 are 1, right? So, suppose that our priority queue is 1,024 elements. Well, that means that we have 256 of each priority. Does that make sense? 256 is priority. Find the expected number of comparisons for insertion. Sounds like a homework problem. Okay, so now what we're going to do, we're going to take a look at that, and we're going to see that analysis tells us that this priority queue of 1,024 elements, basically it has about 10 depths. Maybe 9, maybe 10. Okay, we can use 10 as a nice number. So at depth 9, which is, this is depth 0 at the root, so this is 10, a height of 10, depth of 9 is maximum. At a depth of 9, notice that by and large, on average, all of the priority 3 and 4 elements pretty much will be at depth 9. Does that make sense? And that 50% of the elements are going to be at the bottom level. It's a binary tree, and it's full. So, what's going to be at depth 8? Well, depth 8 will take half of the 512, that's 256. Well, that's all of the priority 2 elements. And finally, priority 1 will pretty much take up depth 0 through 7. So that means if I'm adding a new element, it's going to come out right over here. It's going to become a new leaf on average. Right? That's pretty much what's going to happen. Pretty much, you always get leaves. And if the thing comes up with a leaf, so if I am priority 4, I think I made a slight mistake in the analysis that I'll show you in a second, but we'll fix it right away. If I come in and I am priority 4, under a priority 4, I don't have to do anything. So this is a 4, and I am a 4. New one is 4, just keep it. If I am a 4, and I'm coming, and there's a 3, sorry, said it the wrong way. If I am coming in as a 3, and I go in as a 4, I have to go once. But if I'm coming in as a 3, and there's a 3, you stay. So my analysis, which is wrong, I have to fix it, but we'll do it right now, is the following. So what I'm doing is maybe it's correct. I think maybe it's correct. Now I'm saying it's correct. So the expected number of swaps on an insertion of a priority queue with 1,024 elements for equally likely priorities is 25% of the time I'm going to get a 4. Right? But when I get a 4 will stay at the new location without any swaps. So 25% of the time I get a 4, 0 swaps. Now, sometimes I will get a 3. If the 3 lines up under a 3, 0 swaps. But if it lines up under a 4, 1 swap. But it's 50% chance that it'll be a 3, 50% 4 because it's 50-50 here. So therefore, on average, I would have how many swaps? Half a swap. Okay? If I have a 3 coming in and it goes under a 3, it stays. But if it goes under a 4, it swaps. Since there's equal likely number of 3s and 4s, there's a 50% chance it'll require 1 swap, 50% chance it'll require 0 swaps. On average, half of 1 and 0 is half. So a quarter of the time, it's going to be, on average, half a swap. Now, the next type of element that can come in is priority 2. Priority 2 will need a swap here, anywhere. So therefore, on average, we're not necessarily have all the max values at the bottom. It's not necessarily going to be that way, but it's going to be very close. As n goes to infinity, it's going to tend to approximate that. So, as a priority 2 comes in, it will swap once. How about twice? Huh? No, it doesn't need to. Because once I'm here, so I swap this element for this element, now my parent is a 2, I'm a 2, I stay. There's no violation. So therefore, 25% of the time, 1 swap. Now, then the last one is priority 1. Priority 1 will always swap here, and it'll always swap here, and then it'll stop. You don't have to go on. If you're priority 1, you're not going to beat out anybody here. You're just going to go up so that you are right under a priority 1 element. So therefore, that's how many swaps? That's 2 swaps. So therefore, it's a quarter of 0, quarter of half, quarter of 1, and quarter of 2, 7/8. Is that good or what? That's pretty impressive, I think. So what we have is 7/8. What's 7/8? 7/8 is really behaving, in our example, like a theta 1. Okay? So, I'm not answering this question, but I want you to think about this question. What will happen to our exact heap if we keep adding elements and we get up to 1,000,000 elements, which is 2 to the 20th power? What will happen to our average number of comparisons, average number of swaps on insertion? Okay, I want you to think about that because it's going to be a homework problem. I also want you to think about what happens on deletion. Let's analyze deletion of this problem right here. If we delete something, first of all, how is deletion going to work? Deletion typically works that we remove the root because the element at the top gets served in a priority queue. So we're going to remove the root, which is going to be a top priority element. What do we replace it with? What's our technique for heap? We're going to replace it with the rightmost element of the array. So this max element, which is either 3 or 4, is going to go up here. What is the probability that it's a 3?
50.
What's the probability that it's a 4?
50%.
50%. if it's a 4 element, it's going to swap all the way through here, and all the way through here, and possibly all the way through here. If it's a 3, it's still going to do a very similar kind of. So when we remove an element, our number of swaps is going to be higher than it was for the addition. Addition, the average behavior was 1. What's the average behavior for removal? Well, that's going to be your job to figure it out. And second of all, what will happen when this heap increases to 2 million elements? What will be the complexity of removal? What will be the complexity of insertion? Okay, so we did a heap, heapifying an array from 0, from nothing. We did a heap sort, and we did a priority queue implemented as a heap. That's what we did today. So expect some homework on that topics. Okay? See you.